Hello and welcome to this video on sensor fusion in Julia. Today we will try to estimate the state of a system that looks like in the animation here. So it's some kind of a pendulum-like system. We can imagine it being a simplified version of an inverted balancing bot, like a Segway or something like that. We will today model this system using the modeling language ModelingToolkit. Then we will perform state estimation, and the interesting part of this video is that we will have multiple different sensors that each run on different sample rates. So we will have to perform some kind of sensor fusion. And the sensors we'll make use of today is an accelerometer that is noisy and slow. And then we have a gyroscope, which has nicer measurement readings, and it's a bit faster, but it is subject to some numerical drift over time. And we will take care of that drift by adding a disturbance model to our state estimator so that we can eliminate the gyroscope drift. All right, we start by looking at the modeling problem. So as I said, we will use ModelingToolkit. We load that package. And then ModelingToolkit provides a little macro here. So it provides us with a domain-specific language that looks slightly different from normal Julia code, but it's more suitable perhaps for modeling dynamical systems. So I start by creating some components. These are inputs and outputs that correspond to my control input and my sensors. We have acceleration in X and Y, and we have a velocity measurement. And velocity here in this case means angular velocity. Then the pendulum has some parameters. We have the gravitational constant, length, mass, and some damping. Our variables are the angle of the pendulum, the angular velocity, and the input torque. All right, and then finally we have the equations. And instead of looking at the equations here in code, we will look at the rendered LaTeX form of the equations. So this is perhaps the most interesting equation that relates the angular acceleration to the state variables. And if you're familiar with the dynamics of a pendulum, I'm sure you will recognize this. Then we have the equations for the sensors. So the gyroscope just measures the angular velocity. And the accelerometer, the two different components, have one component that depends on the angular acceleration and one component that is just due to gravity. So the accelerometer always measures gravity. And this is normalized here by G. So this is measuring in units of G. So it's measuring the G-force. All right, I can wrap this dynamics model in a wrapper model that also has an input. So here I just pass a sinusoidal signal to the torque input to simulate something and see how it looks. So I instantiate that model, and then I call structural simplify, which is ModelingToolkit language for take all these equations and figure out a version of this model that can be simulated. And it figure out that, yeah, I need two state variables, the angle and the angular velocity, and these are my differential equations. I can create an ODE problem out of that. I specify the initial condition, and then I can solve that. And it looks like this. So here I start at some angle close to pi and zero velocity, and after a while the pendulum falls down and swings a bit, and then due to the damping, the oscillations die out. Okay, so this behaves the way we would expect. To facilitate working with this model, I create some arrays where I have some measured outputs. So I can measure the accelerometer readings, two of them, X and Y, and then the angular velocity here. And then I also create an array of state outputs. So these are not measurable. I can't measure the angle and the angular velocity, but I will use these outputs for something else later in the video. I will show why. So I put all these outputs in an array, and we now have them here. So they are rendered nicely here in LaTeX. And then I will put this pendulum model in an external model or an outer model later. And then I need to have a different namespace of my variables. So I create a version of these output arrays also where I have this pendulum namespace attached. So that's a technical detail you can ignore for now. Then I have some data I want to perform filtering with. So here I have run the pendulum in closed loop with an LQR controller. We're not going to talk about the LQR control design in this video. If you're interested, it's available here in the end of the notebook. You can go and check it out. But here we have the angle in red. It goes up and down, follows some square wave reference. We have the angular velocity in orange or yellow, and then we have the control input here in kind of dark blue. It's a bit hard to see, sorry. So some version of this data will be used for the filtering, but this is kind of clean, pristine data without any noise and so on. To make this example interesting, we will corrupt this quite heavily with measurement noise and subsample some of the signals. So now we're going to perform our sensor fusion. So what do we do if sensors operate on different rates? So normally we might think of a Kalman filter as something that takes in an array of measurements and produces an estimate of the state. But what if different measurements are available at different times? How do we handle that? Well, I have a few suggestions here. We can use only the lowest sample rate. So if one sensor gives a measurement every second and another sensor gives every 10 seconds, then we could just update every 10 seconds. That's of course very simple, so that's nice, but it also discards a lot of data, so that's we don't want to do that. We could also try to interpolate the slow sensor, so kind of upsample it, and that's also simple, but we kind of have to wait for the next sensor measurement to become available before we know which direction to interpolate in if we don't want to keep it constant. So that's not very nice either. And then the third suggestion here is that we perform individual measurement updates in the Kalman filter at different rates. And that's what we will do in this video. And this has kind of the best of both worlds here. So we can use all the data and we don't have any latency and so on. So we will do that. And it's still, as I hope you will see, relatively simple to do. So here I list a few different situations that can occur in practice. One is that the sensor operating at a slow rate, the slow rate might be an integer multiple of a fast rate. For instance, the gyro is operating on 100 Hz and the accelerometer at 50 Hz. Okay, so that's quite simple, and we would just perform the accelerometer measurement update every second iteration. But sometimes there are no simple relationship between the sample rates. So what do we do then? We might pick a small, I call it a base rate, so that the sample rate of each sensor is approximately some integer multiple of this base rate. That's a simple way to handle that. Sometimes we have stochastic sample rate. So for instance, packages coming over a network and it takes a different amount of time each time. Or maybe we have an event-based system where you only get a sensor reading whenever some event happens. And we can handle that also. Then we just need to kind of use generic integration of the system in the prediction step to handle the fact that we have different sample rates. But that's okay, we can do that. But in this video we will have one slow sensor and one fast sensor, and the fast sensor is an integer multiple faster than the slow one. So here we will now grab our simulated measurement data. So the control input is updated here at the rate, sample rate. The time interval is 0.01 seconds, so that's 100 Hz. And the gyroscope is also sampling at the same sample rate, so 100 Hz. But the accelerometer is only sampling at 20 Hz, so it's 5 times slower. All right. So I grab some control inputs from my from my ODE solution from above. So this is now the control input I will use for the filtering. And then I will grab the data from that correspond to the sensor readings. So for the accelerometer, I will iterate over the solution object here, and I will grab the accelerometer readings. And then I will add some noise here with the covariance matrix that I have picked somewhere here in this notebook. This is the covariance matrix of the accelerometer. And then I will do the same thing for the gyroscope. So I call that Y velocity. And here I have a different covariance matrix, and I have a different sample time here. So this is 100 Hz and this is 20 Hz. And then to the gyroscope, I add a small amount of drift. So here I add a linear drift, 2 times time. So this is just a linear slope over time. And that's quite common. Gyroscopes tend to drift slowly over time. So if we rely on gyroscopes only, we will eventually have a large bias in our estimate. All right, so we look at how this data looks. We have the gyroscope in green, and the two other signals are the accelerometer X and Y. And we see that the gyroscope is slightly noisy, but we have very many measurements. And the accelerometer is also noisy, but the measurements are much sparser. So we only have one measurement from the accelerometer for every 5 measurements of the gyro. Okay, so we'll try to make use of all of this data in our state estimator. All right, in order to construct the state estimator, we need to generate some kind of function that corresponds to the dynamical system. So here I say we want to generate a function f that computes the derivative of the state, given the state input parameters and time. We can do that using ModelingToolkit and the function generate control function. It returns such a function for us. And here I specify what the input is, and here is my dynamical model. And then to make use of this in the state estimator, I need to discretize it. So this is a continuous time ODE. By discretizing it, I get a discrete time system. So this takes the current state and gives me the next state, the state at the next sample time. And I do that using the RK4, Runge-Kutta-4 method here in this case. All right, and then ModelingToolkit doesn't give you any guarantee of what order the state variables come in. But I want to design a state estimator for a particular order of the state variables. So this is when I use this vector of state outputs that I had defined above. So here I compute the permutation matrix that permutes the ModelingToolkit state order to the state order I would like to have. And in this case it happens to be identity because ModelingToolkit picked the order that I want. But I still make use of it because maybe in a different version of ModelingToolkit the order will be different, and then this permutation matrix is important. All right, so to design a Kalman filter or any Kalman-like estimator, I need to specify a covariance for the noise that drives the state. And I can specify that covariance matrix using the variables I'm interested in and then permute it, do a similarity transform with this matrix here and get it in the coordinates that ModelingToolkit has picked. So I say that how to do that here. And then I also ask ModelingToolkit for the initial condition, and ModelingToolkit calls it U0. Maybe I should have called it X0 to align with the notation used in this notebook. But for now, let's call it U0. All right, so now we're gonna construct this state estimator with the two different sensors running at different rates. So I said that the gyro is fast. That's nice. And it has very little noise, or comparatively small amount of noise. But it slowly drifts over time, so that's bad. The accelerometer, on the other hand, is much slower and much noisier, so that's bad. But it has no bias. So each sensor has a number of thumbs up here and a number of thumbs down. Can we combine the information from both of them to get only thumbs up? And the answer is, of course, yes, we can do that. We will do some kind of sensor fusion here. So we will construct individual measurement models for each sensor. And then we will fuse the information from both sensors and the dynamical model here. So we say sensor fusion, but we actually make use of a third source of information as well, and that's the dynamics model. And by fusing all of these sources of information, we get the best of both worlds here, so only thumbs up. All right. So I pick a covariance matrix for my state, and here I have picked some values. I have tuned them slightly. So in the previous video, we looked at how to arrive at an estimate of this using some optimization-based technique. I didn't do that here. Instead, I just picked some values that made the plots look nice. And then I ask ModelingToolkit for a function that corresponds to the measurement model. So here I say, given my system I modeled above, give me a function that takes the state and computes the accelerometer readings. And my input is this torque, tau. And then I do the same, but for the gyroscope. So I want the measurement of the velocity here. Then I pick two covariance matrices for the measurements, one for the accelerometer and one for the gyro. And they actually have the same value here, the covariance matrices, but that's because the accelerometer is measuring in G. So this noise, if it wasn't normalized with G, it would be significantly larger here. Then I construct two different measurement models. So we have both of them are using unscented transform to propagate covariances. Even though I use an unscented Kalman filter here, I don't have to use a UKF measurement model. So for instance, the measurement model for the gyroscope is linear, so I could have used a Kalman filter measurement model for that. But here we use UKF in both cases, or in everywhere uniformly for simplicity. I pass in this function here, the output function. I pass in the covariance matrix. I say how many state variables we have and how many outputs we have. And these here false indicate that this measurement function is not operating in place, and we aren't augmenting the state with the noise variables in this case. Then I pack these two measurement models. Since we now have two of them, I pack them into a composite measurement model that I can put into the unscented Kalman filter. So the unscented Kalman filter takes the dynamics function, the measurement model, and then some properties of the dynamics here. All right, so to simulate this, we now have two different time series with measurements, and they are gathered at different rates, so they don't have the same length. So I've written a little function here that performs this filtering for me, given the measurements of accelerations and velocities. So I start by creating some arrays to store all the data in, and then for each time point in the kind of the base time rate, the base time vector. So this would be the time vector that the input was operating in, 100 Hertz. I grab the current state and covariance and save those in my output arrays. Then if, here is some logic I want to describe here. So if the current time is available in the times that I have acceleration data, then I perform the measurement update with the measurement model for the accelerometer. All right. And if the current time is available in the vector of time points for the velocity measurements for the gyro, then I perform another measurement update. So here I have potentially two different measurement updates, where the gyro will be performed every step in this case, but the acceleration measurement update will be performed every 5th time step only. And then no matter what happens, I always carry on with the prediction step of the Kalman filter. So if I have no data, I only perform prediction, but if I have data from one of the sensors, I perform the measurement update with the corresponding sensor here. And then I package this into a Kalman filtering solution, and we can call that function and visualize the result. So here we see the results. Here we see in green, we have the true state values. So on top we have angle in radians, and in bottom we have angular velocity. So we see that we are going back and forth around pi here. So this would be the upwards equilibrium of the pendulum. And we see that in the beginning it looks reasonably good here. Our confidence bands are kind of including the true state here. But after a while here towards the end, we see that we start to drift away from the true state. So here we are not actually managing to estimate the true state very well. And if we look in the velocity plot here in the bottom, we see that in the beginning we're spot on, but in the end we're starting to drift more and more away. And this is due to this drift of the gyroscope. So we had a slow linear drift. So we see that the measurements kind of drift towards positive values here. But the true velocity is actually slightly different. So we see we have a fairly large difference in between them here. So this looks okay, except for this slow drift over time. So how can we handle that? Another problem is that the filter is overly confident about its estimate here of the velocity. So we see I plot some confidence bands here in yellow. And we see that the confidence bands are quite tight. They include the data here, but they are not overlapping at all with the true value. So it's confident when it shouldn't have been. Ideally, the confidence bands should include the true estimate, the true state here, but it doesn't. So how can we solve that? So we know that the problem here is the slow drift of the gyroscope. Could we potentially estimate the slow drift of the gyroscope? And the answer is yes, we can do that. So we can add a model of the drift to the model the state estimator is using, and let the state estimator estimate also the drift. So what is a reasonable model for drift? Well, if we knew how the drift would change over time, we could just kind of compensate for that, and we wouldn't need a model. But we don't know. We have no idea how the gyro drifts. Maybe it goes up a bit and down a bit, or maybe it only goes up and so on. So the model I will choose to use here is a simple integrator. And what does that mean? It means that the time derivative of the bias here, so this is the state of the noise model here, or the disturbance model. So this xw corresponds to the bias of the gyro. We say that the derivative is 0 plus some random noise. So we say every sample time, every sample instant, maybe there is a small perturbation to the drift. And then we'll try to estimate that. And then we say that the measurement we get from the gyro is equal to the true angular velocity, the thing we actually want to measure, plus this drift, plus this bias, plus some random measurement noise. All right, so now we have random measurement noise plus this estimated bias. So this is now our kind of our sensor model. So I create a new ModelingToolkit model where I have the pendulum just like before, but I also include this noise input W and the state for the drift. And I say here that the drift state, the derivative is only given by the noise input, so the 0 here I didn't include it. And then we say that the velocity measurement is now given by the true velocity plus the bias state. All right, so here we have those in equations rendered in LaTeX. I carry on with the same kind of procedure as I did before to generate dynamics functions and so on. I will not go into great detail on that. And now I have an additional state variable in my estimator. So now I need to kind of augment the covariance matrix for the dynamics noise here. So I take the previous covariance matrix and I concatenate that block diagonally with a small number. So this is now my tuning parameter that allow me to control how fast I want to adapt the drift estimate. So if I have a large value, I say that the drift is changing fast. And if I have a small value, I say that the drift is slow. And here I have picked some value that made the plots look nice. All right, and then I generate this control function. So this would be my f of x upt function. And now before I said this is my control input, now I have an additional argument here saying this is a disturbance input. Because I can't actually control this variable, right? This is a noise term we would like to estimate. So this is not part of my control variable, it's a disturbance input. So I shouldn't actually include that as an input to the generated function here. Then I once again generate two new measurement functions. I grab the initial condition and the parameter array. And then I create two new measurement models, just like I did before, but with these updated functions. Create the composite measurement model and the unscented Kalman filter. So now we're ready to perform estimation just like we did before, but with this updated noise model. And now we see a plot that looks similar to before, but we now have this third state variable that corresponds to the estimated drift. And I've indicated the true drift here with this white dashed line. So we see that the estimate here, it's a rather wide confidence bands, but it generally tracks the drift reasonably well. But perhaps more interestingly is that now I don't have this drift, this bias in the velocity estimates. So we see in the beginning, the state estimator is doing a good job estimating the velocity, and the confidence interval is also including the true state. But also here towards the end, now we see that, if I zoom in here, now we see that the measurements have drifted away. But that's okay, because we know there is a drift associated with the measurements. But the estimate of the state is close to the true state in green. And the confidence intervals are wide enough to include the green line here. So it's okay that the measurements drift away, we know that's expected, but we're still estimating the kind of the hidden true state. So in a practical application, this green line would not be accessible. We don't know that. That's what we're trying to estimate. But our estimate here in this simulation is close to the true value because we have estimated the drift of the gyroscope. All right, so that's kind of a successful application of sensor fusion. We can also compare the errors before and after we added the measurement model. So here I say compute the difference between the filtered state and the true state for the solution I did first and then the second solution. I call them 2 and 3 here. It's a bit unfortunate, but this was the solution without disturbance model, and this is with disturbance model. And we see that I have dramatically reduced the variance here of the estimate. So by a factor of, what is it, 50 or something like that. So a question here towards the end. Do we actually need the slow and noisy accelerometer? If I estimate the drift of the gyroscope, isn't that enough? Do I even need to bother with the accelerometer? Well, we can try and see what happens. So here I have the sample rates of the 2 different sensors. If I increase the sample rate of the accelerometer by 10x, so now we only have one acceleration measurement for every 50 gyroscope measurements. If I save that now and we look at the updated plot here, do we still estimate the gyroscope drift as well? We'll see, it takes a while to update the notebook. All right, we see that, yeah, we still do a reasonable job. But now we see that the estimate here of the angle is starting to drift away, and it drifts away until we get an acceleration measurement. So we see that the acceleration measurement appears at this dashed vertical line here. So we say, yeah, we can do an okay job in this case, but it's kind of an uncomfortable drift here. If we increase the sample rate even more, or sorry, decrease the sample rate even more. So now we get 0 acceleration measurements for the first 5 seconds. We'll see what happens. I know why it's taking a long time. There is an animation being done also each time. We see that now we have a large bias here. We haven't actually been able to capture the dynamics very well at all, or capture this state. So yes, indeed, it's not enough to estimate the drift because we can't properly estimate the drift of the gyro without access to the accelerometer. All right, so let's reset this and go to the closing remarks. So the state estimators we have made use of here, it's a Kalman style estimator. It has a separate step for prediction, where it uses the dynamics model, and a measurement update, where we include information from the sensor. And you can run, for each prediction step, you can run 0, 1, or several different measurement updates. So if you get no measurement at all, then you just perform prediction. If you get one measurement, you run that measurement update. If you get from both sensors at the same time, you run both. And that's fine, so it's very flexible in that way. And here we used nonlinear measurement models, even though one of the sensors actually had a linear output equation. So we can mix and match. It's possible to use a linear measurement update for a nonlinear state estimator if we would like to. And the last point here is that a common solution for this particular sensor fusion problem, where we have an accelerometer and a gyro, is called a complementary filter. And that a complementary filter is performing high-pass filtering of the gyro to remove the drift and low-pass filtering of the accelerometer to remove the noise. But how would you use a complementary filter if the sensors are operating at different rates? Right? So that's slightly more difficult. We could actually say that this Kalman filter we have implemented here actually does implement a form of complementary filter due to the noise model we added. But it doesn't look like the traditional complementary filter, at least not superficially. So this is more of an advanced version of a complementary filter, if you'd like. All right, and for those who are interested, the bottom of this notebook carries out and does the control design that we use to simulate the data above. I will not go into it here, but I will leave the link to the notebook in the notes if you would like to check that out on your own. All right, thank you very much.